In this next part, we'll be doing combinational circuits. We will talk about Boolean Algebra, Karnaugh Maps, and don't care values, minimal coverage, and iterative hardware. Multiplexers, which we have already discussed, we will talk a little bit more about those, and also decoders. Activity levels, enabling, disabling inputs, and also we will talk a little bit about a high-level design, not a very complex design, but we will talk about ways of looking at the design from not at the gate level, but from an upper level. So let's do that, and we'll start with Boolean algebra and talk about the Boolean algebra rules or theorems or laws. Actually, this is what they are known as. The first law is involution, and that is a very simple law. A bar bar, meaning that complementing a variable returns it to its original value. Recall that what we have in Boolean algebra is all the variables have only two value variables, okay, which is 0 and 1. And also the operations for Boolean algebra are bar for complementing, meaning changing a 0 to a 1 or 1 to a 0. A dot for ANDing. A plus for ORing. And so these are the main three operators, and the variables having 0 and 1, these are the rules that we will be discussing. So the first one is a bar bar is the same as a. The second one, a or with 0 is a. When you're looking at that, imagine you have a battery here. That's a very simple way of visualizing it, so that and or will be easily understood. If two switches are in series, they're being ANDed, and if two switches are in parallel, they're being ORed together. So if I have a switch A ANDed with a switch, I'm talking about this one over here now, ANDed with a switch that is always a 1, that means always conducting, then it means that that one switch doesn't really matter, and the result is just that a switch. So a AND with 1 is a. On the other hand, if you think about ORing as having two switches in parallel, okay, where they gonna be turning on a light. Okay, let's draw it a little bit more cleanly. Okay, that's one switch. That's another switch, and then turning on a light. Okay. Now, if you look at this, a or with 0, the upper one is a, the lower one is 0. That means it's never conducting, and therefore, again, the result is just a. And the rest of the laws, you can also visualize it like this, and you can very easily come up with the correct result. So if I have a or with 1 is 1, okay, and a and with 0 is 0. A or a is a, meaning that if there are two switches that are working in parallel, then they both work the same way, then they're just like one variable or one switch. A and with a is a the same way. And A OR with A bar, that means two switches that work opposite and they are in parallel. Well, one is going to be conducting anyway, and therefore it's 1. A ANDed with the A bar, that means two switches in series, none of them are one is always disconnected. That means that you never have a path to turn on the light. A or B is B or A. This is called a commutative law, meaning that you can order the variables any way you want. Same thing with ORing, same thing with ANDing. Associative law, meaning that you can have A or B or C, or you can do A or B or C. Either one is fine. Same thing with the ANDing. Distributive laws. This is similar to the way you do multiplication and adding in regular algebra, but here you're using the AND and OR operator. So A and B or C becomes A and B, A and C, just like multiplication and adding. Or another way of looking at this, going to the left side, is factoring A, B, or C. Okay, and the same thing works for ORing and ANDing. So here you have the first one, you have A or B and C. You can turn that into A or B and A or C. Okay. This is called the distributive law. Absorption law, meaning that you can have A or B. This A or B gets absorbed in A and you come up with A. And then the same thing, A and A or B, that's gets absorbed and that becomes just A. Extended absorption law, A or A bar B is A or B, A and A bar or B is A and B. Okay? Duality means this. If you have an expression, let's for example do this one. This is the second distributive law, right? Which is A and B or A and C. Let's go back and show that. This is what I'm just writing over here. Okay. Is it? I'm sorry, this one. This is the distributive law. Okay. I'm just writing this over here, and this is distributive law, and this is good. Duality says this. It says if there is an expression which is good, like this expression that I have, if you change the ands to ors, the ors to ands, the ones to zeros, the zeros to ones, then the new expression you end up with, that's also a good expression. Okay, well, let's do this. Change the ands to ors. Change the ors to ands. Okay, on both sides, A or B, A or C. Okay, this changes, this changes, this changes, this changes, this changes. You come up with a new expression. That expression is also good. Let's go back and look at the first distributive law, and of course we are seeing that if this one is good, so is this one. Okay, which is what I'm showing over here in yellow. Well, actually you can say this about all the rules that I have shown. Each one of these is the dual of the other one. For example, in this first first complementary law, change the or to and, the 1 to 0 in both sides of the equation. The new expression you get that is also good, and therefore this is called duality. And another rule we have is called the De Morgan's law. And then what that does is, in De Morgan's law, what we have is, it says if you have an expression, whatever expression, a very complex expression, expression 1, ended with expression 2. Now the expression 1 and expression 2 may be very, very complex expressions. And if you bar that, you can write it as expression 1 or with expression 2, and then the bar breaks where you change the operator. And then the same thing works. The dual of this is the same expression. Let me write it in red. If you have expression 1 ORed with expression 2 barred all over, this becomes expression 1 ended with expression 2, and then where you change the operator from left to right, the bar breaks over that operator. And De Morgan's law, again, it has a dual, and you can hierarchically apply that. See, for example, let's look at this. Let's write it in yellow. If I have this expression here, A or B and C, ORed with A okay, if you have something like this and I bar this, okay, and if I bar this, then I'm gonna erase these to make room for this. Okay, the first operator, first you break this at this position, and I probably want to write it like this. Okay, A or B ended with C, or with A bar or B bar, ended with D. There is a bar on top of this. Okay, let's see. First I have A or B and or together. The result is ended with C. These two are or together. The result is ended with D. And then these two are ORed together. The upper level operator is this ORing, and therefore the first place you break the bar is on the upper level operation. Okay, so it becomes A or B ended with C. The bar breaks here and the operation changes to and A bar or B bar ended with D. Okay, so that's where the bar breaks. And then the bar breaks again over this one, and therefore this changes to, let's write it on this side, A or B bar ORed with C bar. Okay, so this bar broke, and then change the operator where it broke, ended with this bar breaks, ORed with D bar, and then the AND changes to OR, A bar OR with B bar. Okay, so that's how you can keep applying the De Morgan's law. And you can further apply that again. You can even go down here and change that to, well, let's go one step further. That becomes A bar ANDed with B bar, or with C bar ANDed with A and with B. The bar breaks and changes both of these little bars, and then ORed with D bar. Okay, this expression and this expression and this, they're all the same thing. All right, so that's De Morgan's, and let's do some examples and show some circuits that benefit from these laws. Here I have V, and here I have A7, B7, and S7 ANDed together, and then A7 bar, B7 bar, S7 bar ANDed together, S7 ANDed together. And this expression requires ANDing and ORing. But see, remember that we talked about ANDing and ORing. We said that we are with CMOS logic, it's much easier to build NANDs instead of and complementing them. So this is a NAND. And if I want to build a 3-input NAND, that's also as easy. All I need to do is to add one transistor in parallel in the top part, and then one transistor at the bottom part, and this gives me a NAND B. If I want to do ANDing, then I have to put inverter, and therefore if I want to build this expression here, I have to have ANDing, then inverting, then ORing, then inverting. So it's going to take too many gates. On the other hand, I can, using the first law, I can put 2 bars on top of this. Putting 2 bars on top of this doesn't change it. On the other hand, changing the lower bar to a broken bar with changing this operator makes it so break this and change this, so it turns it into this new expression here. Now let's look at this. I am NANDing, this is an AND, A7, B7, and S7. I am an S7 bar. I am NANDing A7 bar, B7 bar with S7, and then, so this is an AND, this is an AND, and then I'm NANDing the entire result together, and therefore I'm using 3 NANDs instead of using ANDs and ORs, and therefore I'm reducing the number of inversions that needed to be done. So this circuit on the right hand side is the circuit implementing this V output. And so there are other examples that you can use De Morgan's to reduce the number of inverters, or to turn an expression into some other form to reduce the delay or something like that. Alright, let's do a little bit more exercises on Boolean algebra. Look at this expression here.